Everyone, we continue our calculation example videos for topic 2 PWM technology. So today we have two examples. Let's go over both single phase and three phase PWM inverter and how they operate and how much information we can obtain by observing the PWM waveforms as well as the output. Okay. Example 1 is a single phase 4-switch inverter operating based on unipolar sine PWM technique, and both control signals, triangle signals, as well as the inverter outputs are shown here and here. Okay, so looking for the magnitude modulation indexed MA and frequency modulation indexed MF, and then followed by VDC and output fundamental component frequency and magnitude. Okay, so based on the first graph here, we can find MA and the MF. Okay, so before anything else, you need to recall the formula of MA, which is a ratio between the control signal peak and triangle signal peak. And by reading the graph, the first graph carefully, we can obtain both. So first, by reading the peak value of the control signal, which is here, of course we are seeing one blue and one green, two control signals. That's exactly because of the unipolar PWM technique. So it makes perfect sense for us to see two, and we can just use one of them. For example, we are using the blue, the peak value is here, and by reading the y-axis divisions carefully, we know this value is basically 0.7. So that's the control signal peak value. And in the denominator here, the triangle waveform peak value is as easy as here, which is 1. So we got MA value of 0.7, magnitude modulation index. Similarly, we can read the graph carefully to obtain the MF, which is equals to the triangle waveform frequency over the control signal frequency. So here, be careful, is triangle wave frequency over the control signal frequency, rather than the other way around. So to find the frequency, we can find period instead, which is reciprocal of the frequency, by reading the graph. So first of all, the period of the triangle waveform is basically here, from a starting moment which is 0 to this moment which you need to read. We are not able to accurate this time moment very accurately, but we can fairly say this is about 40% of one horizontal time division. So one horizontal time division is 0.001. So we can tell from here, this moment to this moment, this is about 40% of it. Okay, and then plus the moment at this grid here, which is 0.002, you can come up with 0.0024. This is the period of one full cycle of triangle waveform. Similarly, we read the period of control signal. So be careful, this moment is the time moment for half cycle of a control signal. Therefore, don't forget to times 2. And this moment, the value is basically, I will say, 1/3 of one horizontal time division. So it's about 0.0003. And then plus the time reading here, which is 0.008. You end up with half cycle of control signal is 0.0083. So by this calculation, you end up with around 7 as MF value. We always are trying to have a integer as the result of FMF. Or actually you have one more accurate and more efficient way to find this result, MF, which is by reading carefully the graph, we can tell this conclusion. So 0.5 cycle of VC contains 3.5 cycles of VT, which means your period of VC is as long as 7 period of VT. Therefore, the frequency of VT is 7 times of frequency of VC. Therefore, if you do a ratio between them, you end up with 7. This is more effective, more accurate. And then let's talk about the question B, VDC, and output fundamental components. So here we want to emphasize the concept again. The output graph is here, from where we're seeing square wave like output, because the inverter output cannot be sinusoidal directly. So this square wave contains fundamental component as well as harmonics, and we only talk about the output fundamental component without concerning the harmonics. So the frequency and the magnitude equals to what? So first of all, the frequency of the fundamental components in output is equals to the control signal frequency. This is something we have to know very well, and it equals to 1 over 0.0083 times 2. Yeah, these are the values we obtained previously, and that was 60 Hz. And fundamental component magnitude is equals to another formula you need to know. DC bus voltage value times the magnitude index, which we already obtained previously as 0.7. So what matters is what is VDC value. VDC value can be told by the second graph here, because we know the output, inverter output, is bouncing between the positive VDC and the 0, and then from 0 to negative VDC. Therefore, the magnitude of the square wave in output is nothing but VDC. So it equals to 100. Therefore, we got the magnitude of fundamental component in the output is 70 volt. In other words, this single phase inverter is output a fundamental AC with 70 volts magnitude and 60 Hz frequency. Okay. Alright, let's continue to do example 2, which is for a 3-phase inverter in sine PWM operation. Again, we are seeing two graphs. One is showing the control and triangle signals to come up with the PWM signals. Second is for the inverter output. Okay, following the same idea, we take care of the MA and MF first. And from the first graph here, the MA concept remains same as the ratio between two signals peak values. In the numerator, the control signal peak value. Of course, because we are taking care of a 3-phase inverter, so we are seeing actually 3 different control signal VCs. They are having same magnitude but 120-degree phase shift, one for each phase. So we can just pick one of them to find out the peak value. So by reading this graph carefully, we have blue, red, and yellow 3 VCs, and obviously the blue color, whichever phase it is the easiest one we can go with. So blue one, control signal, is actually this time window is completely exactly one full cycle of the blue VC. so perfect for us to find out both magnitude and the frequency. Okay, so the magnitude, or say the peak value of this blue, is up here. So by reading carefully, this division here is representing 0.8. And in the denominator is easier. The magnitude of triangle wave is just up here, which is 1. So we find out the MA for this inverter is actually 0.8. And the concept for MF remaining same as well, which is equal to the triangle signal frequency over the control signal frequency. And we still have two ways to go with, and the first way is to estimate the period for each one of them, and the second one is to count how many cycles. Okay, so first of all, to find out the period, we can begin with the triangle period up here. So one full cycle of the triangle waveform is beginning from the starting moment, which is, be careful the trick, it's not 0 but 0.01 second, and ended by here. So this time length is the one full cycle period for triangle waveform, and the time moment here at this moment is actually including one full horizontal division, which is 0.001. And this small portion is basically, again, inaccurate estimation is about 25%, or say a quarter of one full division. So it's basically as long as 0.00025. Okay, therefore the full cycle of a triangle signal is this much. 0.01125 is equals to, again, one full division plus this 25% or a quarter of one division. And this moment minus the beginning moment, which is 0.01, equals to the full cycle length. Similarly, for the control signal, again, because we already settled down on this blue color VC, so we can tell the ending point moment is 0.02 minus the starting point moment 0.01 is the full cycle for this blue VC. Okay, 0.02 minus 0.01. So having the both periods, we can find frequency, and then we can come up with estimated MF value, which is 8 integer. Of course, we can try the second way, which is counting how many cycles of VT contained inside of one full cycle of VC. So again, go with the blue VC. And we can count from the starting point. We have one cycle VT, two cycle VT, 3, 4, 5, 6, 7, 8 full cycle of VT. So one cycle of VC contains 8 full cycles of VT, meaning the frequency of VT is 8 times, exactly 8 times of that of VC. So we can come up with 8 directly. So this way is obviously a more precise way and more efficient as well. But if it doesn't work out for you, feel free to use the first way to estimate the periods. Okay. Alright, we can continue to find out the VDC and output fundamental components, frequency and magnitude, from the second graph, inverter output. Okay. So first of all, the fundamental component frequency is always equals to the frequency of control signal. So it equals to 1 over 0.02 minus 0.01. Now these are the values we got from previous step. So 100 Hz is the frequency of control signal as well as the output fundamental component. Second, the fundamental component magnitude follows this formula for three-phase inverter, which is different from the single phase. Okay, this is the formula we need to know very well, and be careful the different factor, square root of 3 over 2. So what we need to know is just the VDC value here, because the MA was obtained from previous step already. So VDC value is the magnitude of the square wave, which is 100 volts, because again the output square wave is bouncing between the positive VDC and 0, and between 0 and the negative VDC. Therefore we can read it as 100. So 100 VDC times MA times the factor in front of it. We end up with 69.28 volts magnitude and 100 Hz frequency for the output fundamental component inside of this square wave. Okay, that's all for this topic. 2 examples for 1 single phase and 1 3-phase PWM. Let me know your feedback. Thank you.